Hi, in this video, we're going to see how to use joint to simulate the bending moment and shear force in Ansys Aqwa. I think most of you already know that in the hydrodynamic diffraction analysis, we already have the bending moment and shear force results for a single structure. However, we have another way, which is using hydrodynamic response and a joint to calculate the bending moment and shear force. To do this, firstly, we need to speed your structure. So in this example, you can see that we already have split this shape into two parts, and I using a joint to connect them together. The type of joint we can select to use in this simulation can be a fixed joint or a hinged joint. So for a fixed joint, it means like your structure will be moved rigidly and for this bending moment and shear force calculation. And for the hinge one, it means there can have flexible motion between your different part of your structure. So for the hinge one, you need to also add in a stiffness onto this hinge joint to represent those flexibility of your structure. So once we have the selection of these two type of joint, we can continue to set our analysis setting for our response analysis. So in this example, I will first try to use the rigid joint. So in here, when we go to analysis setting, we will scrolling down, and we will find there's a axis system for the joint reactions. So in this option, we will have three type of selection for different, and this selection will affect your joint force results. So let's go into see each of them. The first one is the fixed reference axis, which is the global axis, and the next one is the local articulation axis, which is actually a little bit complex in these circumstances. So we first look into the local structure axis. So local structure axis is body fixed axis. So its origin is at the COG center, and the orientation is initially the same as the fixed reference axis, but later when the body structure move or rotate, the local structure axis will move and rotate with the structure and fix on the structure. And then we look at the local articulation axis, and this one will be different depending on different type of joint. So for the fixed joint, and also for the ball and the socket one, for this two type of joint, the orientation of the local articulation joint will be the same as the fixed reference axis, and always the same. So no matter how the structure moves or how the joint rotate, if it is ball and socket one, the local articulation axis of that joint will always the same as the fixed reference axis. However, if the joint is a hinge one or universal one, this axis will move with the structure and rotate with the hinge or universal joint. So it's not anymore the same as the fixed reference axis if the structure has moved and there are relative motion between the structures. The local axis will no longer the same as the fixed reference axis. So, but the same as the more like at least one of the axis will be the same as the structure axis, structure local axis. So then we will need to think which one to use for this joint force, which will represent your bending moment and shear force. If we think through that, we will select the local structure axis. Why? It's because like normally we want our bending moment is in the plane of the cross section of the structure, so if the structure move, like maybe there's a U motion, you need to still be the cross section be the same as the structure will move this with the structure. So we select a local structure axis. You might confuse like, well, that's because the local structure axis is at the origin, is at the solidity center, where that force and moment move to that origin of that axis instead of that articulation where the articulation is. Actually, for the joint force one, no, they won't move to the origin of the axis you selected. It will be always at the connection point of the joint. So no need to worry about that. The things you select here is actually the orientation of the axis. The axis orientation will be used to represent, to calculate the joint force here. So we select the local structure axis in this case for the fixed joint. If you select articulation one, like here, if you select articulation, then the result will be in the global coordinate system. If that is what you want, then go ahead. But if you want the moment always like in the cross section of your structure, then please select the local structure axis. Okay, so then we can go on to add in our results. So what here is like we have connections, go to connections, and then go to joint force, and then we select one of the structure because it's moved rigidly. So whatever structure you select, and select the joint. Which joint it is joint 2. And then you see like here the local structure Z will be the shear force. And then let me duplicate this one. And then for the about y-axis will be the bending moment. So that is one way to do this for the rigidly motion of the structure to calculate the bending moment and shear force. And if you are consider the flexible things, and then you can use the hinge. In this way, we just suppress the rigid one and unsuppress our hinge joint. Here I just use a very simple value stiffness, and in reality you need to select your stiffness like which match the real situation. And here I just take make example, and then in here we for the analysis system axis system this time we can still select the local structure axis, or if you want you can also select the local articulation axis. They will be the same about this y-axis or the z-axis. I think so. Yeah. Because there's no OZ. Yeah. Because there's always like there's no because it is not because the direction we want to calculate is the same. It's always same as the structure one. So yes. So but I would say like why not keep the same, no changes. So still local structure axis, and in this time the direction for the for the bending moment, you need to change to Rx, because the joint axis, rotation axis, is always about x-axis of its local articulation axis. So that's it, how to do this simulation. Simple and quick. See you next time. Thank you for watching.